Hello dear students. Let's have a look at the image that I've given here, or the scenery that is there. We can very well see that there is a horse who is pulling a cart, and the cart is loaded with a few gunny bags of, let's say, a material that is found on the farm. Now the question here is, how much force does the horse need to apply for the cart to move forward? So now let us have a look at what is exactly happening. So the horse pulls the cart with a tensioned rope. And the cart is pulling back on this rope, which is making it harder for the horse to accelerate forward if the cart is heavy. So we can see they have put two tension forces. Now, the horse must push on the ground with the force, more force than it is feeling from the cart in order to accelerate forward. Now, all of you would have gone through a similar experience where you need to pull something behind you. So you would actually be straining at your muscles, with your arms pulling it. At the same time, you would be struggling with your feet too, because you can feel that the feet slips. So we can see what happens. So you can see how much force the feet is applying on the ground, the feet of the horse, for it to move forward. So if the horse is pushing too hard on the ground, it might slip. This is something that all of you would have seen as you're walking. In case as you're pulling, sometimes you would actually slip. So now, let us look at a couple of things that we have to understand here. If you look at this, they have given the cart mass to be 50 kilograms, the mass of the horse to be 300 kilograms, desired acceleration of 1.5 meter per second square, and we have the entire image as a cutout in blue and white. Now, if I look at the tension that is there, I can see the two tension forces that are there, that they are acting opposite to each other. If I look at, that is tension between the cart and the horse. Now, if you look at the weight is 490 Newton, which is acting downwards. If you look at the weight of the horse, it is 2940 Newton, which is acting downwards. Now, if we see the entire thing that is there, there are a lot of arrows that are given here. So what are we trying to look at? Now, in physics, what happens, whenever we are given a set of bodies that are there on which forces are acted, we tend to draw something called as a free body diagram. Now, what does this free body diagram do? It helps us in understanding and analyzing what is happening there. So, for instance, it is a common knowledge that we all have. If this horse should move forward, that means it should apply more amount of force in pulling this cart. Now, at the same time, we have to remember that there is the weight of the cart which is being pulled towards the earth because of its mass. Also, the weight of the horse as it is being pulled downwards. It's a different thing that it doesn't sink into the earth. Now, we will look at the reason why is that. But if we look carefully, we can actually tell that this is how it is going to go. So, only if the horse is able to muster enough strength and apply enough force such that it is able to pull the cart forward without breaking or snapping these strings that are there. So today, let us look at the analysis of free body diagram that is there. So let us look at free body diagram. Now, in physics or engineering, if we talk about a free body diagram, it is called also as a force diagram or a free body diagram, FBD. It is nothing but an illustration that helps us to visualize the applied forces, moments, and the resulting reactions on a body in a given condition. So for instance, if you look at the same image of the horse and the cart that we have, we can see that there is something that is there at the center of this, in the center of this system, which is showing arrows that are there. Now this is a complex system because it has got something called as an angle also in the picture here. but we can try and understand or analyze this in a slightly different way. So we will go ahead and take a very simple picture of a television on a table stand and try and understand what are the forces that are acting on this particular body that is there. So let us begin. Now, if we have to see, now we've got the television on the table, so the best bet is, we know that we'll just talk only about the television here. Now, the television is going to have a downward force, which is nothing but the weight that we know, which can be written as m times g, mass times acceleration due to gravity. Now, if this television has to remain seated on this table, that means there should be some force which is ensuring that it remains there. Because if you look at Newton's third law, for the third law of motion, we have F12 is equal to minus F21, which means we are looking at an action-reaction pair. So that means if I have a force that is acting downwards, I need to have an opposite force which is acting upwards, now which is going to be exactly opposite to the given force. And this force, we call it as the normal reaction force, which we represent by N. Sometimes it is also represented by R, but in general we represent it by N. This is called as the normal reaction force. Now, why the word normal? What is the meaning of this? If I, let's say, draw my x and y axis here. So if this is going to be my y-axis and this my x-axis, I can see that the weight that is there is acting along the negative y. So what I will do is I will extend my y-axis down along the negative axis also. So on doing this, I can actually look at what is the total force that is there. So if we see, I will draw one line which is acting both up and down. And this, if we take it as W is equal to mg, which is acting downward, this we call it as the normal reaction force. Now if you look at the angle, with respect to the horizontal, the angle formed is 90 degrees. So in math or in physics as such, we call this 90-degree angle as the normal. That means any line which is perpendicular to the surface, perpendicular itself would mean that you form a 90-degree angle. It is called as a normal line that we have drawn. Hence the name normal reaction force. Now here if I see, the TV is balanced on the table. And if it has to be balanced, it basically means that the weight that is there, which is equal to mg, is equal to the normal reaction force that is there. So in case of this television that is there, we can see that the weight is balanced by the normal reaction force. Now let us try and understand this same criteria of writing forces when a body is moving. Now here if we see, in this case our television was stationary, so we didn't have any other force that was there. But what happens if our body is moving? So for instance, let us take this car that is there. Let us assume it is moving forward with a given velocity. Let us take it as, let's say, 10 meters per second. Now, we know that if this vehicle has to move forward, then the back wheels or the rear wheels are the ones that are pushing it forward. So it has a force that is applied which makes sure it moves forward. At the same time, since the wheels are in contact with the road, it is going to have friction, which is going to be opposite to the force that is there. Now, we have the weight of this car and the normal reaction force, because of which the car doesn't sit flat on the road or doesn't get sucked into the road. So what we can do is we can explain this using a small representation that is there. So let us assume that this red box that is there is our car. And if I go ahead and draw the free body diagram, so what I will do is I will just draw a plus. Now the idea of a free body diagram is always the forces that are there, we can tell that they are concentrated at the center. So if I draw this, so the center of mass that is there, it is concentrated there. And the entire force that is acting seems as if it is acting at the center of mass. So we had a force F, which is making sure that this car is moving forward. We had a frictional force, which I'll write it as F small r, which is acting backwards. We have the weight, W equals mg, acting downwards. And we have the normal reaction force. Now for this car not to topple or not to slow down when it is in motion, all these four forces have to be balanced. Because if you look at the previous case, we have seen that the television that is there is balanced because the normal reaction force and the weight are equal. So right now, if we have to try and balance this, we will just try the expressions like this. So normal reaction force is equal to the weight, which is equal to mg, and the force will be equal to the frictional force for it to be in equilibrium. So here we are looking at equilibrium of forces. We are not trying to solve anything as of now. So we're just trying to find out what happens in these cases. Now, one thing we have to understand, if the body has to accelerate, then we need to apply a higher amount of force. That means the force should be greater than the frictional force. Now, in order to, let's say, strengthen this understanding, let us have a look at a small example. So here we have a doll that is there and a box. Now let us see when is this box going to move. So I'm going to apply the force. So we have both the forces, see the frictional force and the applied force as the free body diagram that we have drawn. And let us see. Now you see that it starts moving. So when the applied force is greater than the frictional force, that is when the body starts moving. And if the applied force is much greater than the frictional force, you can see that the body starts accelerating. Now that you can look at it with the background. So the moment the person stops applying the force, it is only the frictional force that is there which brings this body back to rest. So right now, yes, it has come back to rest. So whenever we are looking at forces, we have to understand what is happening in a free body diagram that is there. In general, when we are trying to understand, let us have a look at it in terms of the masses. So this is a 50 kilogram mass that is there. And let us look at what happens to the sum of forces that is there. So this person is applying the force. It is going to move. So I have applied a huge amount of force. Let us give the values that are there. So for instance, right now, since it has moved, we know that 94 was the frictional force. Let's have a look. So this person is applying the force. Now, the applied force and frictional force is one and the same. Now, as we increase, we can see that the sum of forces increases. The friction becomes 94 Newton, whereas the applied force is 131 Newton. And as the applied force increases, much greater than the frictional force, it can move much faster. So the maximum force here that I can procure is close to 500 Newton. So till now we have always looked at a force on a flat piece of land that is there, or a flat bed that is there. It can be anything. It can be on a table, on the ground, on the road, anything, but we have taken everything flat. Now if you remember the horse and cart diagram, we had something called as an angle, theta. So here we have to look at what happens to the forces when we are looking at an inclined plane. So we can draw an inclined plane which is roughly looking like this. So this is an inclined plane. That means there is an angle between the ground and to where we've kept this. Now in this, suppose we have to calculate or we have to look at the forces that are there. We can draw one, let's say, box that is there over here. And now let us look at the forces. For this we have to understand one thing. We will have to look at a couple of things. The first thing is, since angle is given, we have to look at resolution of vectors. That means I am going to resolve my vectors that I get here. So all the forces that are there are nothing but vectors, because it is magnitude. The force value is there, it's a magnitude and applied in a particular direction. So this is the first thing. The second thing that we have to see is, since it is on an inclined plane, how will the forces act? Action of forces. The third and the most important is the direction of acceleration. Whether it is accelerating downwards or upwards would depend on the external force that is applied. So once, let's say, we dissect this and we have the free body diagram, then we will go ahead to look at how we can equate and calculate the respective quantities that we would like to find out. So for this, let us draw an inclined plane again. So this is our inclined plane. Let us go ahead and draw a box. We can have anything. Now why I am taking a box is it is simple for us to understand. So if we have this as our box, the first and the foremost thing that we have to draw as soon as we get this kind of a thing is, we will just make sure we mark the angle. Now we don't know the value, so we will leave this as theta. But if we see, we have the most important force, which is the normal reaction force. Now under any circumstance that is there, this normal reaction force will always act perpendicular to the surface. True to its word, it will always act perpendicular to this surface. So this is not going to change. Another force that is there is nothing but the weight. So what I will do is, since we are taking it from the center of mass, just get rid of this part. Yes. Now, the weight that is there is always going to act vertically downward, irrespective of this angle that is there. So W is equal to mg. So that means from this we can understand that the weight is not directly balanced by the normal reaction force as it is happening in the previous cases. Since we have an incline, we need to figure out what is the force that is balancing the normal reaction force that is there. Now let us assume that we have the body moving downwards. So the acceleration is, let's say, downwards. So if the body is accelerating downwards, then I will have the frictional force that is in between the box and the surface that is acting upwards. So far, so good. We can see that the acceleration and frictional force, they are kind of balanced each other because they are in two opposite directions along the same line. That is, acceleration is downwards, friction is upwards. But the normal reaction force here is an unbalanced force. Now, in order to balance this, we will use the idea of resolution of vectors. So in order to understand this, what I will do is, we will do the resolution of the vector. Now we are going to resolve the weight that is there into its respective components. So if we can draw a triangle here, let's say, which is looking like this. Now we have both the components here. How we can do this is, we take this angle theta to be present here. So that means the angle between the actual weight and the component of weight is taken here, which is similar to this angle of the incline. So this I can write it as mg cos theta and this vertical component as mg sin theta. So now if you want to complete this diagram, we can generally write this right here without having this. So we will redraw this diagram with all the forces that are there. So I can go ahead and write this component down here in green, and I can put my sin theta component here, which is along A. So I can rewrite this as, I have got mg cos theta because this is the angle theta, and I have got mg sine theta. Now to balance these forces, since we have resolved the components, now we can simply write the normal reaction force is equivalent to mg cos theta, and now here if you see along the horizontal, I've got frictional force. So I'll take Fr is equal to, I have got mg sine theta and acceleration in the same direction. So I'll simply write mg sine theta plus A. So this is how we resolve the components for a body that is moving downwards in direction for the applied force. So now here we know that the frictional force that is there is nothing but the coefficient of, let's say, since it is moving, kinetic friction times the normal reaction force. So Fr, I can write it as mu k times mg cos theta. Now since the body is accelerating downwards, we have to calculate what its acceleration is. So for that, I will just rewrite the expressions. N is given by mg cos theta, and Fr was given as mg sine theta plus acceleration, and Fr was equal to mu k times N, which is nothing but mu k times mg cos theta. Now we can just substitute that here and calculate acceleration. So the acceleration will be nothing but Fr minus mg sine theta, which is equal to mg cos theta, so there's a mu k here, minus mg sine theta, which is nothing but mg times mu k cos theta minus sine theta. So this is the acceleration of a body when it is moving downwards. Now this is one of the cases that we can look at, which is again motion along a straight path, but here it is at an incline. Now what happens if you're trying to look at the same thing with a pulley system? As most of the cases that we might encounter would be related to the pulley system. So let us have a look at what we get when we look at a pulley system. So we can go ahead and look at this pulley system that is there. So here if you see, you have got a pulley of radius r, you have two masses m1 and m2, and from this it is very visible that m1 is greater than m2. So keeping this in mind, let us see the first thing that we are going to do. We will as usual go ahead and draw our weight first, which is acting vertically downwards. So this is going to be mg, we take it as m1g, this is going to be m2g, which is going to be w1 and w2. So w1 is equal to m1g, w2 is equal to m2g. Now if you see, in both the strings what is happening, it is, let's say m1 and m2 is connected by the same string, and since it is a string, it is going to have tensional force that is there. That means the tension will always be acting upwards. So this will be the direction of my tension. So if I write this as T1 and T2, I mean it's not wrong, but let's have a look. I will tell that T is equal to T1 is equal to T2. That means I am taking both the tensions to be equal to T. The reason why I am doing this is, it is the same string that is connecting both M1 and M2. So if you see, it is the same string which is going and coming on the other side. So therefore, the tensions are equal. So instead of writing T1 and T2, I can simply write this as T. Now both the tensions are acting upwards because they are opposite to the direction of the weight that is there. But if we see, M1 is moving downwards. So therefore I can tell my total acceleration that is there. I'm going to have two different diagrams here now. One case for M1, the acceleration is downwards, whereas in M2, the acceleration is upwards. So we can classify this as A1 and A2. Now by how much it is going to accelerate is something that we can calculate. So free body diagrams are generally drawn even for this kind of a system, which is a pulley system that is there. This is a little more simple when compared to the inclined plane that we just took, because in an inclined plane an angle comes into the picture, but here this is devoid of angle. So the idea here is we can calculate what is the tension and what is the acceleration that is produced. It can be acceleration for both the blocks separately or for any one of the masses that can be calculated. So let us move on and try and see how we can calculate this. So let us go ahead and do the calculation. Now here what I will do is I will calculate acceleration for m1. Now the same thing can be applied for m2 also. So in order to calculate acceleration for m1, if we see, we will have to write the equations that balance it out. So the first idea that we have to understand is, since the tensions are the same, the amount m1 moves down is corresponding to the amount m2 moves up. That means the distance m1 will go down is the same distance that m2 will come up. For instance, if we have seen someone drawing water from a well, we can see that the force that is applied to pull this, let's say, bucket up will be equal to the force with which it comes up, or the rate at which, or the speed with which you are pulling it down, the rope is going down here, is the speed at which this one ascends. So here, instead of writing a1, a2, we can simply write it as a. So we can find acceleration of the total system that is there. Now for this, just like how we have done previously, we will write the equations. Now if you see here, for the first part of it, let us look at it for m1. For m1, if we see, we will have m1g, which is acting downwards, plus m1a, that is the acceleration. Instead of a1, I'm taking it as a. Now both are in the downward direction, is equal to tension, which is in the opposite direction. I'll take this as equation 1. Now the idea in solving this is, you might have various methods in the textbooks, but the simplest way of understanding is, you add up the forces which are there in the same direction and you equate that to the forces in the opposite. So if you see here, m1a and m1g are in the same direction, so I've added them. Tension in the opposite, so I put it on the other side. Now let us look at for m2 what happens. Now when we look at for m2, m2g is the only one that is acting downwards, but our tension and acceleration is acting upwards. So that is going to be equal to T plus m2a. So I have got two equations. Now the second equation that is there, we can do a small change. T minus m2g is equal to m2a. Now the reason why I have written it like this is, if you see, the acceleration is going to be upwards. That means, according to the force diagram, the video that we saw, applied force was greater than the frictional force, that is when it moved. Now the same thing here. The acceleration should be upwards. That means the tension should be greater than m2g. So the tension minus m2g, whatever is the resultant force, if tension is greater, m2 will move upwards. So that is why I have rearranged it like this. Now we have equations 1 and 2. We can just equate them because both are equal to tension, or I can substitute equation 1 in 2. So I will end up having m1g plus m1a minus m2g is equal to m2a. So I've got m1 in terms of g and a, m2 in terms of g and a. Our idea is to calculate the acceleration. Now we can do a small rearrangement for our expressions. The reason why is, we need acceleration to be downwards in the first case and acceleration to be upwards in the second case. So the understanding from the animation that we saw with the frictional force and the applied force was that if the applied force is greater, the body is going to move. So in this case, if my body needs to have acceleration, m1 needs to have acceleration, that means the weight applied should be greater than the tension. Similarly, on the other hand, the tension should be greater than the weight of the second block if the acceleration has to be upwards. So what we will do is, We will do slight modifications for these expressions and we will write them like this. So m1g minus t is equal to m1a and t minus m2g is equal to m2a. And what we have done, we have removed the forces, or we've subtracted the forces to get our accelerations. So if I take this as equation 1 and this as equation 2, now we can solve for t. So on adding equation 1 and 2, I will get m1g minus t plus t minus m2g. What I've done is LHS and RHS I'm adding. So m1a plus m2a. So here t gets cancelled. I will end up having m1g minus m2g is equal to m1a plus m2a. Our goal is to calculate acceleration. So this can be written as m1 minus m2 of g divided by m1 plus m2. So now in order to calculate the tension, we can substitute in any one of the equations that we have. Let us substitute in the first expression. So T will be equal to, or let's say m1g minus the tension will be equal to m1 the acceleration. Now acceleration we have found it to be m1 minus m2 by m1 plus m2 of g. So m1g minus t is equal to m1 of m1 minus m2 by m1 plus m2 times g. So tension, I can write it as m1g minus, I have got m1g of m1 minus m2 by m1 plus m2. Now I can take m1g common. I will have m1g of 1 minus m1 minus m2 by m1 plus m2. So the tension is going to be equal to 2 m1 m2 by m1 plus m2 of g. So this is the tension and acceleration for the case of our a body that is, let's say, suspended using a pulley. So two bodies suspended using a pulley. Now let us look at another case of the pulley system that is there. So here we have two bodies connected by a string, but one body is placed on a table. So let us go ahead and analyze and see what is the free body diagram for this particular case. So if we take for the first body, we know that there is a force which is pulling it forward. We also know that it has the weight that is acting downwards, the normal reaction force that is acting up. Now for the time being, we will go ahead and ignore friction. We will assume that the friction is very, very small. So as to keep things simple. So normal reaction force N, this is going to be m1g, and this is going to be m1 times a, the acceleration forward. On the other hand, if you look at m2, I think we will look at tension also here, which is acting in one direction. So if you look at m2, we have tension which is acting upwards. Now along with this, we have the weight which is acting downwards, m2g, and therefore it has a total acceleration which is going to be downwards. So that I can write it as m2 times a. So now we have our free body diagram, we have all the forces that are there. Let us go ahead and calculate the tension and the acceleration that is there. For the first body, I can simply write tension is equal to m1a, because there is no force that is acting backwards. So frictional force is absent. We can assume that this table is smooth. Since we are not talking about friction, it's a smooth surface. Now this is going to be my equation 1. Let us look at what happens to the second case. So T minus m2g is going to be equal to m2 times a. If it has to move downwards, then this is the equation that we have. So equating 1 and 2, we get m1g is equal to m1 plus m2 of A, or acceleration is equal to m1g by m1 plus m2. Now we can go ahead and look at what is the tension that is there. And the tension is going to be m1 m2 by m1 plus m2 times g. So here are a few questions. It says two masses m1 equal to 12 kilograms and m2 equal to 8 kilogram are connected to two ends of a light inextensible string passing over a light frictionless pulley. Find the acceleration of the masses and the tension in the string when the masses are released. Through what distance the 12 kg mass would fall in 0.3 seconds after the masses are released. Take g equals 9.8 meter per second square. So if we look at the diagram, we have got a pulley here with two masses. So this I will take it as m1, and this, the second mass, I will take this as m2. So we can go ahead and draw the free body diagram for this. So in the first case, if I take m1, this is going to be W is equal to m1g acting downwards, the tension is acting upwards, and the total acceleration m1a is acting downwards. In the second case, I will have W2 is equal to m2g, which is acting downwards, the tension acting upwards, and the acceleration m2a acting upwards. So keeping this in mind, we can go ahead and write our equations for tension for both of these expressions so that our forces are in equilibrium. We have m1g minus tension is equal to m1a. This I can take as the first equation. And T minus m2g is equal to m2a as the second equation. We can add equation 1 and 2. So I have m1g minus T is equal to m1a and T minus m2g is equal to m2a. So on adding, I will get m1g minus m2g is equal to m1a plus m2a, or m1 minus m2 of g is equal to m1 plus m2 of a, or a is equal to m1 minus m2 by m1 plus m2 into g. So this is the acceleration. Now let us substitute and let us find out. Now we know that m1 is given as 12 and m2 is given as 8. So 12 minus 8 by 12 plus 8 into 9.8. So the acceleration will be 1.96 meter per second square. So we have calculated the first part, that is acceleration. Next, let us look at tension. Now for tension, we can take any one of the equations and we can substitute acceleration. So let us take the first equation, which is m1g minus T is equal to m1a, or T is equal to m1g minus m1a, which is nothing but m1 of g minus a. m1 is 12, g we've been given as 9.8, acceleration we just found it to be 1.96. So on solving, we get 94 Newton. So the tension is 94 Newton. So according to the question, we had to calculate what is the tension that is there and the acceleration. Both we have calculated. Now we need to figure out what would be the distance that the 12 kg mass travels in 3.3 seconds after it is released. That means initially both the masses were held, and when the stop clock started, the masses were released. So at 0.3 seconds, at what distance would the heavier mass travel is something that we have to calculate. Now for that, we can try and look at one of the equations of motion that is there. So we can look at S is equal to ut plus half a t square. Now t is given as 0.3 second. Initial velocity is 0 because initially it was at rest before the experiment was started. Acceleration we found it to be 1.96 meter per second square. So on substitution I will get S is equal to 0 plus half into 1.96 into 0.3 the whole square, which will be equal to 0.088 meter, or we can write this as 8.8 centimeter. So therefore we have found the tension is equal to 94 Newton, the acceleration 1.96 meter per second square, and we finally found the distance to be 8.8 centimeter. In this question it is given that a block of mass m slides down a smooth inclined plane as shown. Now the forces acting on it are the normal reaction force and the weight, which is given as mg. The acceleration of the block is a. So two students analyze the situation and apply Newton's second law. Now we have to figure out which of it is correct. So if you look at it, first student, mg sin theta is equal to ma, and the second student has written mg n cos theta is equal to ma sin theta. Now let us draw the free body diagram for this and let us understand. So we can go ahead and draw the diagram here itself. So we have our mg, which is acting vertically downwards, and the normal reaction force which is acting like this. So this is going to be the normal reaction force. This is going to be equal to mg, and this is going to be our acceleration ma. Now if we see, we have to resolve the components. So on resolving the components, I will have this as mg cos theta with this angle, and along this is going to be mg sin theta. So if you look at the first student, what has he done? He has written mg sin theta is equal to ma. Now what is the understanding of this? Now specifically they have mentioned one important point here. It is Newton's second law, based on application of Newton's second law. So the second law is nothing but F external is equal to mass times acceleration. So if you look at this, the first student has written exactly that. So what has he done is, the student has written F external is equal to mg sin theta, and this is equal to ma. So if you look at this, this expression is absolutely correct. Now let us look at what the second student has given. Second student has given mg minus n cos theta is equal to ma sin theta. Now again, if we are going to look at the second law, I can write this as F external is equal to ma. What has happened? The component is taken. But what is this n cos theta? Now we know that mg is acting downwards, correct? Now n cos theta is along the direction of mg. So instead of resolving mg, the student has resolved n cos theta. So it is like telling the student has applied, the second student has applied the relation F external is equal to ma in the vertical direction. while the first student apply the same expression in the horizontal direction. So here we can see that the direction in which we are applying our laws are also very important. So both the expressions that are there, that is mg sin theta is equal to ma, and the second one, both are correct. So in this case, both the students are reporting the right thing, but the reasoning has to be given that in which direction they have measured for the Newton's second law. So in this question, they have given that there is a body of mass m1, which is 10 kgs, is placed on a smooth horizontal table. It is connected to a string which passes over a frictionless pulley and carries at the other end a body of mass m2 of 5 kg. What acceleration will be produced in the bodies when the nail fixed on the table is removed? What will be the tension in the string during the motion of the bodies? And also when the bodies stop. So this is the diagram that has been given in this respective question, where M1 as 10 kg is placed on the table and M2, which is 5 kg, is suspended. So you can see that the direction of acceleration they have marked, tension, the normal reaction forces R also they have marked, the weights are also given. So let us try and solve this. Now the first thing that we have to see is, you need to figure out what is the acceleration produced. So what do we have? M1 as 10 kilograms and M2 as 5 kilograms. Acceleration due to gravity is given as 9.8 Newton per kg, which is another way of writing meter per second square. So this is an SI unit only. You need to figure out what is the acceleration and what is the tension. So for this, let us first look at the acceleration, which is produced because of the second law of motion. Which is F equals ma, which we can write it as m2g is equal to m1 plus m2 of a, which implies a is equal to m2g by m1 plus m, which is 5 times 9.8 divided by 5 plus 10, which we will get it as 3.27 meter per second square. So acceleration part was fine. Now they would like to know what will be the tension in the string during motion of the body and also when the bodies stop. So here if we see, there is tension in the horizontal direction as well as tension in the vertical direction. So first we will look at tension in the horizontal direction. So if I'm looking at tension in the horizontal direction, we are basically looking at this expression. T is equal to m1 times a, where m1 is 10, acceleration is 3.27, which we get it as 32.7 Newton. Now, previously when I had given the explanation, I told that it is the same string that is connecting. So therefore the tensions must be the same. So in this numerical, we can try and figure out if both the tensions are the same or not. So along the horizontal, we have found what is the tension. Now let us look at tension in the vertical direction. So I will have m2g minus t is equal to m2a, or t is equal to m2g minus m2a, which is nothing but m2 of g minus a. So here tension is going to be equal to 5 times 9.8 minus 3.27. So we will 32.65 Newton. So approximately it is 32.7 Newton. Now suppose we have T prime as the tension when the body is moving and it comes to rest. So what is happening? It was moving and T prime is the tension developed when it comes to rest suddenly. So as it comes to rest, I can tell that the acceleration is 0. So therefore, the net force on both the bodies is equal to 0. So hence I can write T prime is equal to m2g, which is nothing but 5 into 9.8. So T prime is going to be 49 Newton, that is there. So now at the end of this, we have looked at how to draw free body diagrams. We have taken different cases. We also looked at different numericals. Now it is time to go back to the horse cart arrangement that we began with and look at what are the forces that are acting on the horse, on the cart, and on the entire system as a whole. So here let us see what are the forces that are acting on the horse. So there is the tension of 75 Newton which is acting backwards, that is towards the cart because of the string that is tied. The weight is 4900 Newton, so the normal reaction force is also the same, and the force that is applied by the horse is 825 Newton. So to obtain an acceleration of 1.5 meter per second, a horse of mass 500 kg is applying a force of 825 Newton to a cart of mass 50 kilograms. Now there is no angle. That means I made sure that the cart that is there, so this you see these strings that are there that are attached to the horse, these are parallel to the ground. So the moment we take angle into consideration, that is when we take the resolution of vectors, look at the sine and cos component, and based on that we are going to calculate. So this is only for the horse. Now let us look at the cart. So if we look at the cart, the weight and the normal reaction force are 490 Newton, whereas the tension is 75 Newton. So it's the same as tension that is applied from the horse on the cart for this particular string. Let us look at what is it as a whole. So as a whole, for both of these together, we've got the weight, which is 4900 Newton, is equal to the normal reaction force. Now we have got the force 825 Newton, which is actually applied forward for this cart to move. So the balance is there so that we can make sure that the cart moves. Now if you look at the smaller arrow, it is nothing but the weight of this cart that is there, that is 490 Newton, as it moves forward. Now let us just change the angle a little bit and let us see what our values change to. So now let us introduce a small angle. Let's say an angle of 10 degrees. Look at how much change has taken place. The tension is now 76 Newton. The weight and normal reaction force remains the same. So also the force that is applied forward. So this is on the horse. Let us look at what happens to the cart. So if you look at the cart, this was our initial value that was there. That is 490 Newton as the normal reaction force and the weight. Now here you see the normal reaction becomes 477 Newton and the tension is 76 Newton. So what has happened? Because of this 10-degree angle, there has been a change in the weight that is there. That is the normal reaction force because we have to take the component. Similarly, if you look at the total weights that are there. So the weight and the normal reaction force, let's say the weight for the horse remains the same, 4900, whereas the normal reaction force becomes 4913 Newton, which is different from the case when the angle was 0. So like this, when we introduce angle, that is when we take sine of the component or cos of the component, there is always bound to be some change compared to when all the forces are in equilibrium without any angle that is present in between.